So this is the last tutorial of semester 1, and we're going to discuss number sets. So there are a variety of numbers you might pick. A very natural one to start with are the natural numbers. Which is the set of strictly positive whole numbers, labeled with this bold type n. And the key operations you can do on this space is to add and multiply. Now, if you wanted to subtract, you need the space of all integers. Written z. These are all the whole numbers. And you can see here that you can subtract any two numbers and remain in the same set. You can still add and multiply. But we can't divide yet. If we wanted to divide, we would use the set of rational numbers. The rational numbers Q is the set of quotients. P over Q, where P, Q are integers, and Q, the denominator, is non-zero. And here, you notice that we can divide. And as a remark, see question 6. P over Q is equivalent to A over B, that is, two rationals are the same, if and only if BP minus AQ, that is, you cross multiply, is 0. And that just says that something like 2 over 4 is equal to 1 over 2. We also have the real numbers. So these are all the numbers on the real line. So there's 0, there's 1, but there are many more. The proper formal definition of this is beyond our scope. And the irrational numbers those are the real numbers which aren't rational. And so we have some strict conclusions. Overall, we have that the natural numbers, so that's 1, 2, 3, and so on, are contained in all the integers, but aren't equal to those, which are themselves contained in all the rational numbers, again, not equal, and those are contained and not equal to in all the reals. And this difference here are those irrationals. So let n be a natural number, so that's a positive whole number, or it could also be any integer, in fact. If n is divisible by 2, then we say it's even. And if it's not, we say it's odd. But let's explain what it means to be even a little bit more formally. That is, there exists some k some integer k such that n is equal to 2k. That's how we describe even numbers. So we can say that otherwise n is odd. So that's if it's not divisible by 2, or if there doesn't exist some integer such that n is equal to 2k. You can see that equivalently, there would exist some k belonging to n or z such that n is equal to 2k minus 1. Note that I'm going to use 2k minus 1, not 2k plus 1, because you want 1 to be odd. And because 0 isn't actually a natural number, you don't want the odd numbers to start at 3. So let's just give two very concrete examples over here. So for the even case, 24 is equal to 2 times 12, and 37 is equal to 2 times 19 minus 1. So in the case where you use all integers, you could use 2k plus 1 here, provided you stuck with all integers. Because then, for instance, 1 would be 2 times 0 plus 1. So what are some properties of odd and even numbers? We've already used this in the past, but we're going to do things a bit more proof style. So the sum of two even numbers let's prove that it's even. And similarly, you could do it for odd or even cases. So let E1 and E2 be two even numbers. Then, for some K1 and K2, whole numbers, or integers depending on which we're picking, the even numbers must be 2 times those respectively. And let's just look at the sum. So it's 2 times k1 plus k2. So we found a number k1 plus k2 such that this one, the sum of the two even numbers is equal to 2 times that. And by our definition of being even, this means that the sum is even. So, presumably, you can try out the other cases. So let's do a slightly more complicated proof. No rational solutions to x squared minus 2 is equal to 0. Let's give that a star for this particular equation. So our aim is going to be to prove that this quadratic equation, so prove that star has no rational solutions. So let's prove it. And our style is going to be a proof by contradiction. So what does that mean? That means that we're going to suppose that star is true. So secretly, no, it can't be true, but we're going to suppose it's true, i.e. x squared minus 2 equals 0 does have a rational solution. That is, x equals p over q solves star with p, q integers and q greater than 0. That's the condition to be rational. Sorry, q not 0. Either is okay. We can further assume by the cancelling down law that p and q have no common factors. We seek a contradiction. And that would mean that our initial assumption is false. How are we going to do that? We're going to show that P and Q must both have 2 as common factor. And so it contradicts the statement that they have no common factor in common. So in general, when you're writing proofs, often it's very good to tell the reader what you're going to do. Like, this is the core idea of the proof, and then now we do the nitty-gritty. So our initial equation was x squared minus 2 equals 0, so we plug that in for x equals p over q, with q greater than 0, or non-zero. And so we have that p squared is equal to 2q squared. You note that this means that p must be even. Because if it's odd, an odd number times an odd number is odd. Maybe you can prove that part. So if p were odd, if you squared it, it's still odd, but that can't be right because the right-hand side has a factor of 2. Therefore, p is equal to 2k for some integer k. In fact, so plugging this back in to this line here, this implies that 4k squared is equal to 2q squared. Dividing by 2, you get 2k squared is equal to q squared. And by exactly the same argument as this, for applied to this time Q instead of to P, the same argument implies that Q must be even. So now we have that P is even and Q is even, and that's our contradiction. They both have 2 as a factor, and so have 2 as a common factor. And this negates our initial assumption that they were cancelled down as much as they could be. We were allowed to do that for free. It contradicts P and Q have no common factors.